Hello, everyone. Welcome to the next joint meetup organized by quantum computing groups from Washington, Warsaw, and Toronto. My name is Pawel Gora. I will be the moderator of this meeting today. I'm a CEO of the Quantum AI Foundation, which is the organizer of the Warsaw Quantum Computing Group meetup. And today we have a pleasure to host a great speaker, Yuval Boger, Chief Marketing Officer from Classic. So Yuval will also introduce briefly the company at the beginning. And the title of the lecture that will be given today is Creating Quantum Circuits for Hundreds or Thousands of Qubits. So it sounds very interesting. This meeting is recorded, so as usually the video will be available later on our YouTube channel. And if you have any questions during the meeting, please post your questions on our chat. So we'll ask the questions at the end during the Q&A session, but also we discussed with Yuval that if you would like to ask something during the lecture, you can also unmute yourself and interrupt. So then this meeting will be more interactive. But if there are no urgent questions, then it's better to post them on our chat. Before we start, I would like to also say a few words about our future meetings that we already have in plans. So the next meetup will be on 29th of January, and the title is Genetic Optimization Acceleration Using Quantum Annealer. So the speaker is Vinay Fadnis. The next meeting will be in February, 26th of February, and Dr. Kamal Choudhary will give a talk, Quantum Computation for Predicting Electron and Photon Properties of Solids. We would also like to thank the sponsors of this meetup, Quantum AI Foundation, Warsaw Quantum Computing Group, Zen for Quantum, Quantum Computing and Data Science Group from Toronto, OrionX, Association Quantum, Cambridge Quantum, Q Egypt, and Q Mexico, which are Q cousins of the Q-Word organization. All right, so now I will stop sharing my screen, and Yuval, the Zoom is yours. Thank you once again for accepting our invitation.
That's perfect. Thank you so much, Pawel, and thank you, Helen. My name is Yuval. I'm Chief Marketing Officer of Classic. Classic is a software company. We're headquartered in Tel Aviv. We make a software platform that, as I hope I'll show you, makes it easy to create sophisticated quantum circuits. And my details here, yuval@classic.io, on Twitter, Qubit Guy. And we're hiring. If you're an engineer and wants to work in quantum in Israel, we're hiring. If you want to work in our marketing organization in the US, we're hiring as well. So would love to hear from anyone by LinkedIn or email after the call. So just a little bit about Classic, founded in 2019. As I mentioned, based in Israel in the US. We've got about 30 quantum software engineers today, lots of patents that we filed, and live customers, customers with live installations in both industries and academia that are using our platform. So you're in the quantum meetup because you've all heard the hype about quantum computing, how it's going to change the world, how it's going to revolutionize everything, how it's going to allow for better option pricing and creating new batteries and what have you. But it's not, don't believe all the hype, but certainly some of the hype. So when you look at quantum computing, we see that it is starting to enter the mainstream. Last month, Zapata released a survey of about 300 different enterprises talking about where they are in their quantum computing journey. We see that just over 29% of those surveyed are either early or advanced adoption stages of quantum, so they already are working. About 40% are planning to adopt quantum computing in their company, and 30% don't have current adoption plans. And I think it's fair to say that The impact of quantum could be transformational, just like web technologies or just like machine learning and AI, but big revolutions take time. So what's holding back? And on the right side, you see many of the companies, I'm sure you know, that are working in quantum computing. So what is it that's holding quantum computing back? So the first thing that's holding quantum computing back is the hardware. If you think about last year, we sometimes say that when boys grow up, their toys just become more expensive. And so quantum computing were really expensive toys. And I call them toys, especially the gate-based machines, because when you have up to, say, 50 qubits, then anything that you can run on a quantum computer, you could simulate on a classical computer. And of course, classical computers are cheaper, they're easier to use, they're more prevalent, and so on and so on. But as we enter this year, we're going to start seeing computers with more qubits. IBM announced 127 qubits. Called Quanta and Atom and others are saying, oh, we've got 100 qubit computers and so on and so on. And so with the increasing number of qubits, we'll be able to do more. We'll be able to balance larger portfolios. We'll be able to simulate better, larger molecules and so on and so on. So obviously one thing that's holding back is the hardware, and not just the number of qubits, but also whether it's the noise or the coherence or sort of the connectivity, other hardware parameters of quantum. The second thing that's holding back quantum is the talent. This is a slide from McKinsey, and it's basically showing that McKinsey expects in 2025 that more than 1 out of 2 open jobs for quantum computing will be left unfilled. So McKinsey is saying there are going to be 10,000 open jobs and only 4,300 people that can take these jobs. So if you're a company, you want to get into quantum computing, you want to hire quantum engineers, if they don't exist or it's hard to find, that's holding back quantum computing. The good news, according to McKinsey, that in 2030, this gap is primarily being closed. And there are a couple of different ways to close it. We can talk about them later. We see the top universities, whether it's UCLA or MIT or Harvard or others, are starting quantum computing curriculum to get more engineers and more scientists into the workforce. And of course, the other question is, do you really need a PhD in quantum physics to work in quantum computing? And we believe that we're helping address that question as well. But the other thing, the thing that first and foremost we like to talk about is the software. The software is holding back, or is potentially holding back, the development of quantum computing. And let's see why that is the case. So I think we can agree that hardware and software are interconnected, right? Even if you had a perfectly error-corrected 1,000 or 10,000 qubit machines, if there's no way to write software for it, then that hardware is useless. So hardware and software need to be developed together, and software needs to support the ability to write to create quantum circuits for these larger computers. At Classic, we trust the hardware vendors. So we look at, IBM and Amazon and Google and IonQ and Honeywell and Atom and Cold Quanta, and we know that they will deliver. It'll take a little bit more time or a little bit more time, but they will deliver larger and larger computers. So we're not worried about the hardware. We are seeing, of course, a large variation, both in the modality of the hardware, as well as the number of qubits, the noise characteristics, the connectivity, the native gate set. So there are a lot of variations between hardware providers, but the hardware will be there. But if you had a computer with 1,000 qubits, can you write software for it? Are you ready for it? So here's this is an illustration of a 1,000 qubit circuit. Do you feel like you can create one of those? We think the answer is, with existing platforms, the answer is no. We believe that with today's development methods, it's impossible to create large quantum circuits. So when you look on the left side, you see sort of a 5 qubit circuit, something that you could find in an IBM Quantum Challenge or a couple of years ago. And that's fairly easy to create manually. When I was a boy, my parents got me an electronics kit, and it had AND, OR, XOR, NOR gates, and I could build a little circuit. Maybe I could build a counter and so on. But could I use that same manual technique to design a CPU? I mean, we're all on Zoom. We're using billion transistor CPUs. They're not designed by manually connecting the bits and the gates together. So when you go from that 5-qubit circuit to sort of 25-qubit circuit that you see here in the middle to 1,000-qubit circuit, things get more sophisticated, things get more difficult, things just become more difficult than a typical or any human could do. It's a little bit like running 100 meters. You know, many people can run a 100-meter race in 20 seconds. Very few people can run it in 10 seconds or less. No one can run it in 5 seconds. So there's just a limit to human ability. Well, let's look at a couple of examples. So here's a really simple example. Here is a Grover circuit, a 3-qubit Grover circuit. It's trying to find an oracle to mark states 101 and 110. This is taken from one of the IBM Qiskit tutorials. And when you look at a circuit like that, that can be hand-coded. You could say, okay, I'm going to connect this qubit to this gate to that gate, and so on. So when you look at how such a circuit looks in Circ, I could have the Q-sharp implementation or the Qiskit implementation. You're basically seeing that it's appending circuits, it's appending gates to the circuit. It's creating a circuit, and then it's appending a Hadamard, and then it's appending a CX. And then so it's basically manually defining the connectivity between the qubits and the gates. We don't think that scales, because previously we saw this sort of simple oracle where you just wanted to create just to mark 2 states. But what if you have a more complex oracle? So here's an example. Let's assume you want a Grover search that looks at, that finds A, B, and C. A is a qubit register that's 2 qubit wide. B is 2 qubits wide. C is 3 qubits wide. So for sort of regular math, that's simple. For quantum math, the oracle that I want to generate is what's written on the screen: A plus B plus C and 15 modulo 8 XOR 3, and so on and so on. I want to create a quantum circuit that marks the states that meet this oracle. Well, here is such a circuit. And this is actually, here's such a circuit created by Classic. You see these as high-level blocks, by the way. If you go one by one, you can say, here's the addition, and here's the AND, and here's the XOR. If I take it one step deeper, I could zoom in on the addition and say, oh, the add block is done here with QFT, with quantum Fourier transform. I can zoom in more, see how the QFT is performed, and so on and so on. So even for this not too complex, but certainly more sophisticated oracle, the circuit becomes complex. And so it becomes difficult to create such a circuit by hand. And let's explore a little bit more what these challenges are. Why do we have these challenges? And obviously what we can do about them. By the way, am I speaking too slow or too fast, or any questions that I can answer at this time?
In my opinion, it's fine. There's one message on our chat.
Okay, let me try to open it. I'm sorry when I'm
yes,
presenting.
so it's a question about topological quantum computing, but I don't think that it's very relevant to what you are talking about now. So maybe we can just keep it for the Q&A session at the end. Very good, thank you. And sorry, I have full screen for the presentation, so I don't see the chat very well right now. Don't worry. So yeah, if there are some important questions, then we'll try to interrupt.
Excellent, thank you. So we were talking about design challenges. So what do you do when you want to create an algorithm in quantum computing? So first you come up or find a recipe, the steps that you need to do it. So this is, of course, a sophisticated algorithm. This is in derivative pricing algorithm from Goldman Sachs, University of Maryland, and IBM. And we see in this particular article in section 5.2, you could find it on Google. It basically says, okay, here are the individual steps that you're taking to implement this algorithm. So we look at step 7, we control copy all registers containing such and such, and then every single step is a set of things that you have to do to implement this algorithm. So the process looks something like this. You define the desired functionality, control copy or whatever it is that they said. Usually you find a pre-existing scheme or algorithm. Maybe someone published a blog that does a QFT, or maybe someone did this, the other. You try to modify and adapt them for a specific use case, right? Maybe I found a Grover search, but now I need to write the Oracle. And then you work to optimize the circuit. Once you have that circuit optimized, you move it on to a compiling stage, whether it's a Qiskit or Q# or directly to Bracket or an IonQ and so on. And so the first 4 stages are essentially manual. You're doing them manually. The compiler is automatic. But when you implement each of the individual steps, you have to make a lot of different decisions. There are decisions at the block level, each of these steps, and then there are decisions at the system level. So the block level decisions could be, each of these blocks might have multiple implementations. So for instance, just if I take a simple thing, I want to say, I want to create an adder. Well, an adder could be a QFT adder, or it could be a Ripple adder. I was looking the other day at Wikipedia, and I was looking at sort, just classical sort, number sort algorithms. There are about 42 different algorithms listed there. Well, why 42? Well, they're 42 because every algorithm has some advantages over another. One of them is the fastest, and one of them is the most predictable, and one of them works well if the numbers are already pretty much sorted, and one of them, and so on and so on and so on. So, while we don't have 42 different algorithms to implement a quantum adder, at least I'm not aware of them, each of these functions has multiple different implementations. Then you can say, well, let's think about auxiliary qubits, ancilla qubits. Sometimes if I have more auxiliary qubits, I can make a shorter circuit. I can make the circuit simpler. But maybe I don't have enough auxiliary qubits. Maybe I'm limited in the total number of qubits that I have in my system. You can also say, how accurate does this block need to be? So for instance, let's assume you're doing option pricing and you're trying to simulate a Gaussian distribution. Well, at what level of accuracy do you need this Gaussian distribution? I'll show you an example later about state preparation. You say, well, here are the probability mass functions that I want to load into the qubits. How accurate do you need them to be? So that's a decision you have to make at the block level. But then when you take all these blocks and try to put them into one coherent system, you might say, oh, I don't have enough qubits. I'm running on a 20 qubit machine and I've just created an algorithm that does 27 qubits or 200 qubits. Well, I need to take it down. You can worry about the depth of the circuit. Oh, my circuit is too long because it's too deep. It's just not gonna run. I'm gonna have coherence issues, noise issues. Which qubits can I reuse and which can I not reuse? If I want to reuse a qubit, I need to uncompute it. Then you have to think about the hardware. You know, what is the native gate set? What is the noise model? What is the connectivity? And the worst part is that these issues are deeply interconnected, because when you say, oh, I have too many qubits in my circuit, now you need to go back to the block level and say, oh, so could I reduce the accuracy? Could I choose an implementation that has fewer qubits? How do I do that? And this becomes, it's fairly simple. I mean, for you guys, smart people, it's fairly simple when you have 5 qubits. It's impossible to do it manually when you have 500 qubits. So we think about life that in this way. We think there's a multi-dimensional design space, right? I could, for a given algorithm, we could do versions that have more qubits or fewer qubits, deeper or not deeper, this implementation, that implementation, and so on and so on. It's almost like asking, what's the best car? There is no one answer to what's the best car. The question is, the best car for what? Is it the best car to haul cargo across the country? Is it the best car to drive as fast as I can on an Autobahn in Germany? Is it the most fuel efficient car? There is no one answer to the best car. It depends on the requirement. You could say, I want a bigger engine, but then I'll have worse fuel efficiency. So the same thing with quantum. When you look at the design space, there are so many different parameters that you can play with. Now, when you do it at the system level, at the functional level, you have a lot of freedom. Say, I could choose a different implementation. I could reuse this qubit. I could do this, that, the other. However, when you do it at the compiler level, when you already are giving a circuit to, not to pick on IBM, but to a Qiskit compiler or a Q-sharp compiler, there's not that much they can do. Yes, if they identify two successive Hadamard gates, they could cancel them out. And yes, they could certainly work with the connectivity and they could try to do some optimization, but the compiler doesn't know what is it that you're trying to achieve. And therefore, the flexibility that the compiler have is much, much, much lower than the flexibility that you have earlier on in the process. So let me try to give a few simple examples on what that looks like. Let's assume that you have a simple function, and that function has two inputs and two outputs. You can see each of these sort of bluish block is one instance of that function. Two inputs, two outputs, and one auxiliary qubit. So a native implementation, and you want to run that function 3 times. So a native implementation could be what you see on the left, just use 9 qubits, and I'm all good. Well, if you only have 8 qubits, then you could say, I'm going to take, do you see that in the middle? I'm going to take the output. I'm going to take the auxiliary qubit output from the second function. I'm going to uncompute it and then use it again. Or you could even compress it into 7 qubits. So even with a very, very, very simple function, there are different ways that you can arrange them. The same things happen when you have Hamiltonians. You could say, I've got a local Hamiltonian and I'm going to do trotterization. I'm going to say, I could say, oh, here are the 4 parts. I'm going to do them sequentially, but I could make a circuit not as deep by doing them, by arranging them a little bit differently. So I'll show you in a second. When you have, you want to do, say, a square b plus b square a, you could do it with more qubits or with fewer qubits, depending if you're willing to uncompute some of the qubits. So you got all these trade-offs that are going on all the time. And so just to summarize, and here's, by the way, 2 versions of the arithmetic operation. One that the lower one is shorter, is not as deep, but uses more qubits. And the top one is deeper, but uses fewer qubits. And they both achieve the same functionality, just with different constraints. And so just to summarize the challenges, to get quantum computing to where we all want it to be, we need to be able to build quantum circuits that scale, quantum circuits that take advantage of 100 or 1,000 qubits. To do that, we have to navigate a really huge design space because we got so many degrees of freedom that we could do. As humans, we could only explore a handful of options. We have a lot of different constraints that we have to think about: number of qubits and coherence and depth and native gate set, which, and by the way, a circuit that may be best for an IBM computer may not be best for the Honeywell computer, and may not be best for the IonQ computer, and so on and so on. And last, which touches sort of on one of the first points that I made, that there is a problem in finding and hiring people that work in quantum. One issue is that to do quantum today, you need to almost have PhD level experience in quantum information science. So if you think that it's difficult to find a quantum scientist to work for you, how difficult would it be to find a quantum scientist that also knows supply chain, or that also knows chemistry, or also knows finance, so you can sort of combine all these issues. It's almost like when you want to design a web page. Today, a web designer can just work in Figma or in some graphical software and design the page. The web designer does not need to understand C++, certainly doesn't need to understand assembly language or how the CPU works. So once you start separating, once you start abstracting the layers, and you have access to more people, because you don't expect someone to master the entire compute stack. So if I may, I'd love to describe for you how we at Classic think about solving this problem. Pawel, is that okay? Or were there questions that you'd like me to address in the meantime?
No, so as for now, I don't see any questions that we should address now. So yes, please go on.
I would like to hear
Or maybe someone has a question. Yes, go on.
No, I would like to hear the approach that sorry, I'm not getting the name of the person. Yeah, the Classic took, because I find this quite interesting. If you can continue on that line of thought, that'd be great. Thanks.
Very good. I shall do that with pleasure.
And Yuval, maybe you can also include, you're probably heading to this, and it's probably on the company's site, but all those customers you talk to, when they're getting a solution from you, what are they getting? A box in consulting, and access to the cloud? What's that solution look like? This is very intriguing.
Sure.
So address that later or during your talk.
Happy to answer it now and talk about it later as well. We create a platform that allows designers to create sophisticated quantum algorithms with ease, or with relative ease. So what they get from us is a software license. They get a license to use the platform. It's almost like, here is a CAD software, and now you can design whatever you want on it. So they get a license to use our platform. We're not a consulting company, we're a software company. And so when customers work with us, they might certainly choose to do a proof of concept where they say, oh, by the way, show us that you can do this. But even when we do a proof of concept with customers, our goal, of course, our goal is to make sure that we've solved their problems, but our primary goal is to make them self-sufficient with the platform. So they don't need us. We're there for support, but they don't need us to code the algorithms for them. They can code and develop their own IP and their own algorithms.
But implied in what you're saying, just to be clear, that software license would come with some training, I imagine. I mean,
of course, yeah.
All right, okay. With
training, documentation, with support, everything you need. But ultimately, our goal is that the customer does the work on their own, and they don't need us on an ongoing basis to do the work for them.
Okay, thanks. That makes a lot of sense. Very clarifying.
And well, I believe you are abstracting the hardware level as well. So I can write one programming language and it can work on multiple hardwares, maybe IBM or Package, wherever. Is that right?
Sure. So we integrate today. I mean, you'll see that our output could be in multiple languages. We output in CASM, we output in Q#, we output in Circ. We can connect already with AWS Bracket, with Azure Quantum, with IBM, with IonQ, and with others. So, and just to make sure, the circuit that we generate might end up being different for each of these hardware providers because the constraints are different or the desires of the designer are different. But yes, you could do end-to-end from creating an algorithm to executing it on the cloud or on or in a simulator with our platform.
Okay, one follow-up question. So let's say I'm writing some code on your platform. Can I translate that into the Qiskit format so that I understand it better?
Yes. Yes,
Okay,
and I'll show that in a bit. Yes. So what we do in a nutshell, and then we'll go in much deeper into this nutshell, is we synthesize gate-level circuits, we synthesize quantum circuits, we generate quantum circuits from high-level functional models. And functional model is about what you want the circuit to do, as opposed to how exactly is the circuit constructed. And because we do that, we believe that we enable the design of complex quantum circuits. And so when we thought about the problem of how to create circuits for 500, for 1,000, for 10,000 qubits, we looked at history and said, where have we seen this problem before? Is there something we could build upon? Is it something that could serve as our inspiration? And we found that we can have a lot of inspiration from electronic design. So what you see on the right is a circuit. It's not a quantum circuit, it's an electronic circuit, and or NOR XOR gates. And this baby has 100 different gates. Do you know what it does? I don't. I mean, I know now, but I didn't when I saw it. Do you think you can change it? I can't. But how was this circuit created? Well, this circuit was created with a high-level functional model. And in the electronic design world, you see those called VHDL or Verilog and others. And so the code on the left was used to automatically generate, to automatically synthesize the circuit on the right. So if you look on the code on the left, all of a sudden you say, oh, I've got ports and I've got signals and I've got a carry and I've got, I mean, I can start to understand what's going on in this circuit. If I needed to change it from 16-bit, it looks like a 16-bit something, right? It says, 15 countdown to 0, or I could change it pretty easily and I could test it. I go back to us running Zoom on billion transistor chips. When someone wants to design a chip, they don't start at the individual gate level. They say, oh, I want memory and I want a USB controller and I want a power controller. And then the USB controller is broken down into certain functionality and so on and so on. So this is what's being done very, very successfully for tens of years on the electronic design side. And so you have companies like Cadence or Synopsys that take the VHDL or Verilog and synthesize it into an electronic circuit. Well, guess what? We do the same for quantum. So here is a functional level description of a Grover operator. And so you see it says function Grover operator. Inside it's got a functional block called the oracle. And here's a simple oracle function, a plus 5 XOR b modulo 8 equals 2. And then our platform can take this high-level functional model and generate, if PowerPoint cooperates, and generates a circuit that matches these requirements. And by the way, one other thing that you may have seen there, I've also defined a couple of constraints here, qubit counts, for instance. I want 12 qubits, and I could vary that and see if I can make it work with different types of qubits. So where our software sits in the quantum stack, we built this, what we call a synthesis engine, and it takes two inputs. One is the high-level functional model, just like I showed you. And the other is a set of constraints. And the constraints could be anything from the number of qubits to the preferred gate set to accuracy and many, many, many other things that you say, well, this is important for me to generate a design that meets these constraints. These constraints could be at the block level, could be at the system level. And then we automatically explore thousands and thousands and millions of different options and come up with, or try to find at least one that meets your requirements. And then our output is in one of, Qiskit or Q# or Cirq or Bracket, and which then goes to the compiler or transpiler and then can be executed on the cloud. One of the questions that we often get is, how hardware aware are we? And the answer is that we don't have to be, right? So I can generate a circuit that you can just say, oh, I want to run it on 27 qubits, and we'll generate a circuit with 27 qubits. But when we do work with hardware vendors, they might say, this is what you should know about my hardware. I don't have CZ gates natively, I have CX gates. These qubits are noisier than others. I have 60 qubits, 40 are noisier and 20 are less noisier. So take that into account in your optimization, in your synthesis. We don't have to do that, but certainly helps. The more we know about the system, the better the output is. And so instead of having the process that I described earlier, the manual process where you define the desired functionality, look for blocks, modify them, optimize the circuit, and you do all that manually, we sort of flipped it around and we say, just define the desired functionality. And we have a library which continues to grow. And by the way, you can add your own blocks. So if you have, I was giving the adder example as a QFT or ripple adder, you've got a different type, no problem. Insert that as one additional implementation. And then that's one more thing that we can explore when we synthesize the functional model into the gate level. And so because we do that, we allow the designer to achieve certain advantages. Focus on what you want to do and not how. Build sophisticated circuits that scale, because just like you've seen in earlier, I could put a very sophisticated oracle, or I could put many, many blocks together. We've seen that our optimization can dramatically reduce, sometimes by orders of magnitude, the number of qubits in the depth of the circuit relative to what a human would do in sort of a naive implementation. Because the circuit generation is very quick, you can dramatically reduce the development time, because today you could build a circuit manually and then say, oh, too many qubits. Now I have to go back and work another week on changing that. Well, that we compress that dramatically. So if you're doing say a proof of concept, or you're trying to figure out something in your enterprise, you could do a whole lot more in the same amount of time. And because we abstract a lot of the quantum specific complexity, all of a sudden you can be a finance expert, or a supply chain expert, or a chemistry expert, or a quantum or a machine learning expert, and generate useful circuits without having a PhD in quantum physics. And because we are a software company, not a consulting company, you keep your own IP. Whatever you create is yours. We don't have to see it. We don't have to know it. There's no risk that this somehow gets to another customer. So let me show you an example. The example I showed before, we delivered the platform in two ways, or in both ways. One as a Python SDK, and the other in a VS Code, Visual Studio Code environment that's very interactive. The code fragment I showed you before was in VS Code. Now I'll show you some Python code fragments. And this is to solve a 3-SAT problem. A 3-SAT problem is one, or an NSAT problem in general, is one of these NP-complete problems. It basically says, find the set of variables that satisfy multiple constraints. And here's how we set this up. So for instance, in the first we say, okay, you've got 3 variables, x1, x2, x3. These are the 3 constraints that we want to satisfy. The first one is x3 is 0 and x2 is 0. This is the second one, and third, and so on. I could make this as complex as I want. So this is how we set up the oracle for this 3-SAT problem. This is the code. These 2 lines here are the code that generate the circuit with a certain constraints. So it's qubit count 13 and maximum depth, and then this would be to basically execute the circuit. So if there's 3 parts, not too many lines of code, we have a quantum solution to a 3-SAT problem. And I want to show you 2 of the outputs there. I could show you more, but 2 of the outputs from the exact same code, only by changing the constraints. So this particular one was optimized for circuit depth, to make the circuit as shallow as possible. And this one uses, as you can see on the left, Q0 to Q12, so 13 qubits, and you can see sort of the high-level blocks. We run it again, and this one is optimized for qubit count. So this is a deeper circuit, but it only uses 8 qubits. So we can go from this to this really in a few seconds. And as a designer, that allows you to find the best operating point for you. So how would customers use Classic? You almost can think about Classic as MATLAB, where you say, here's a super powerful underlying engine that could be used for multiple applications, and then application suites. So on one hand, you have the core synthesis engine, but then we have functionality where we say, oh, we've already implemented value at risk. We already have this code that helps you find the ground state of a molecule. Here is what you do for optimization, and so on and so on. As I mentioned, you can build and create your own functions. So you can build your IP, reuse it, change it easily, and run on the back end of your choice. So for instance, this is what a value at risk financial services application would look like. This is the Visual Studio Code example, 20 qubits, max def. We want a finance function with a log normal distribution. We're trying to find European call option. If you look at these lines again I'd say from line 4 to the end, there's nothing quantum about it, which sort of, I'm trying to make the point that you don't have to be a quantum expert to use our platform. And here is a different example. In this case, this is the Python code that does a Qubits-based portfolio optimization. So the code is on the left, the circuit is on the right. And let's see where I am here. So we believe that we do have the technology today to allow 1,000 qubit or 10,000 qubit circuits. And we believe that by doing that, we're solving 2 of the 3 problems that are holding back quantum computing. One is, how do you write software for these complex machines? And 2, do you really need to be a PhD in quantum information science to do so? And with that, why don't we take a few questions, and then I'm happy to show a live demo of what the software looks like.
Okay, great. Thanks, Yuval. So it looks that currently we have plenty of questions. So let's maybe go back. I'm not sure if this one has been asked and answered. Do you have any plans to integrate Classic with TKET? I'm not sure what is TKET, which optimizes circuits for any platform.
So
it's a question from Mark Jackson.
Mark, hey Mark, we're happy to talk to you about that. I mean, we can output, you can almost think about it as output styles, right? Just like we can output to Qiskit and QASM or AWS Bracket, we can work with you to output in the format that you like, and then you can take the next step, which you guys are expert in, and add your significant value to the optimized circuit that we generate.
Okay. All right. Next question from Tom. I think that there was already an answer during the lecture, but let's ask and clarify. Is the platform pure web-based, or is it possible to get a local copy of the software to run interactively with other software of our choosing?
Yes. So the way we deliver it is as follows. So the user interface is certainly local, whether it's VS Code or you can run Python locally. The circuit generation, every time you generate a circuit, by default, it goes to our servers in the cloud, just a SaaS model. But if that's a concern, then we could work with you to generate or to host, for you to host a local copy of our server. So data wouldn't, even the circuit design would never need to leave your enterprise. But even when we work in a SaaS model on the cloud, what you get back is the quantum circuit. And then you can execute it wherever you want, however you want. You can execute it locally on a simulator. You could go to the cloud provider of your choice and so on.
Okay, great. There's the next question from Bernd. Is the Xanadu platform also supported?
I don't think so, but I'll have to check and get back to you on that.
Okay, good. There's a question from Rupesh regarding slide number 40. So maybe if you can go back to slide number 40, there's a question, what is the max depth, then :1 Probably there was something like this on the slide 14.
Sure. So max def is a constraint, and you can say, I want a circuit that's not more than, say, 200 steps deep. So it's a constraint to our engine to say, how deep are you allowing the circuit to be? And I think one of this easy way to think about it is usually there's a trade-off between number of qubits and the depth of the circuit. And you could say constrain one and open the other, or constrain both. And by the way, if you constrain both too much, then we may not be able to find the solution. Maybe no one will be able to find the solution. But that's what that parameter means.
Okay. There's the next question from Itamar. Are you using results from combinatorics?
Could you explain, Itamar, what you mean by that?
Maybe
I'm not sure I understood the question.
Yes.
Yeah. You're talking about many constraints and huge design space. Now, combinatorics or theory of probability is dealing directly with questions like that. And they have amazing results that may or may not be so easily implemented here, but may help or give some hint.
So Itamar, this is the part of the presentation where I say I'm just a marketing guy. I mean, I do have a master's in physics, but let's assume I'm just a marketing guy. So let me check that and get back to you offline on that question, because I'm not sure. Please.
Another one, please. If you talk about many qubits in the future, and you are preparing us for that, how about people talk about error correction, but I'm interested now, what if one or more of the 1,000 qubits is a little bit slow or defected, I mean, in trouble? Do you have fault tolerance process to cover this, to handle this, to think about that?
So I think you're opening a very big and a very interesting topic about what happens when you have a lot of qubits. So for instance, let's assume that today the limit of classical computers is to simulate 50 qubit machines. So, and now let's assume you used our platform to build a 200 qubit circuit. How do you debug it? Are you just going to run it and see if it works? And then, I mean, it's not as simple as classical computer where you can set a breakpoint and say, oh, what's the value of X? And let me change it, and so on and so on. So without going into the answers right now, that's certainly something that is keeping us busy, thinking about how do you debug? How can you test parts of the circuit? What happens when you have more and more information about particular qubits, and so on and so on. Obviously, by the way, we spoke about functional blocks, so you can say, I've created my own error correction algorithm, and I've used this functional block, and now I'm going to insert it in various stages in the algorithm and use the classic platform to see what happens there. So I hope I answered at least some of your question in that regard.
Yes, I just want to add one more point, that this is connected to my first question in the sense that, again, probability and combinatorics may put some bounds on this possibility of, let's call it, failure.
Okay, very good.
Yuval, we have several more questions, so would you like to try to answer now? I think let's proceed with the questions. So the next two questions might be also a bit too technical, but let's try. How do you search for all the possible circuits that match the constraints and implement the desired function before outputting the optimal circuit?
So I'd like to answer that question in two parts. So first, how we search is sort of the part of the core technology of Classic. And so how do we explore? How do we find the constraints? How do we look at alternative implementations? how do we do it relatively quickly, that you can create a circuit in a few seconds. That's definitely a significant part of our IP. And so I'm not going to be able to answer exactly how we do it. But the second part of the question dealt with saying optimal. And sometimes we asked, can you prove that this is optimal? I think that what we look is not so much at optimal, but it's something that meets the constraints. So for instance, you can say, create the circuit in 20 qubits, and we'll create it in 20 qubits. Now you could change it very quickly and say, now create it in 18 qubits, or create it in 15 qubits, or create it in 10 qubits. And at some point, we're going to say, no, we were not able to find the solution. But if you said 20 qubits, there may be a 15 qubit solution, but as long as we meet the constraints, then we're happy with it. You can almost think about it as a local minima as opposed to a global minima that is the absolute optimal circuit.
Okay, there's the next question that is quite relevant, and maybe the answer has been already provided. Is the optimal circuit always produced or just near optimal? And how is the optimality of a circuit measured?
So the optimality of a circuit is measured by meeting the constraints. If we create a circuit that on one hand meets the functionality and on the other hand satisfies the constraints, then we're happy. And so same thing, I mean, you could say, just to give an example from another field, I'm creating code for a microcontroller and I've got 64 kilobytes of ROM, and if I manage to fit the program in that, then I'm happy. And if I'm not, then I can change the optimization and say, now make it smaller, or so on and so on.
Okay, there's the next question about optimization. What are the quantities one can optimize other than depth and qubit count?
Well, you could control a lot of different things. You could do depth and qubit count. You could do accuracy. I'll show you that in a second. You could control the preferred gate set. You could control the level of entanglement. And so there are many, many other parameters that you can control, but you're right. Qubit count and depth are usually the most popular.
Okay. There's another question that seems to be quite general and high level, but let's try. QDL for quantum computing is in the same level as VDL for electronic circuit design. Is it possible to build an even higher level language for quantum computing like C or Java? I'm not sure if we can answer this question.
When I think about higher level, you could say, for instance, company X is a company that are experts in financial services. They can take our platform and build even a higher level set of functionality that say, just give me your portfolio and I'll optimize it. Or if it's a transportation example, just give me the routes that your truck needs to stop and the optimization criteria, and I'll find the best solution. I'm not sure whether C++ is sort of higher level or lower level than VHDL. So, but I think you can certainly climb up the stack on the application level and say, oh, I'm going to make this even more specific to a particular application by using the underlying classic platform.
Great.
I think it's to do with the abstraction. How abstract can you make a language? And on that matter, I think maybe I would say Q# is slightly more abstract in the sense than going in that same direction as the question being asked, I would imagine.
I will show a little bit later in the demo, I will show Q# code that we generate from the platform. And I think it ends up being longer. So I think with a few lines of classic QDL code, you end up with quite a few lines of matching Q#. So if that's the metric, then I think we're more compact and more abstract.
Okay, great. There's the next question from Barry. Is there any non-commercial access to your software for students?
Talk to me about that offline, and this is something we're working on to provide to certain universities and others access to the platform. Absolutely.
Okay, great, thanks. The next question about certification. Do you have any plan for classic certification similar to Qiskit certification?
Not yet, but that's a great idea that we're thinking about.
Okay, great. Is there a sandbox on Classic Cloud that is provided?
I'm sorry, a book?
A sandbox. So I get that by sandbox.
Oh, sandbox. I'm sorry.
Yeah, sandbox.
Yes.
Sorry.
Yes. So you can run. Together with the platform, you get a simulator, and yes, you can execute the circuits on a simulator. It could be our simulator, it could be someone else's simulator, but yes.
Okay. There's the next question about the combinations. How do you guard against unintended consequences, particularly rare but long tail combinations? So it's a question from James. Mm-hmm.
So James, could you explain to me what you mean by unintended consequences, please?
Yeah, I'm just thinking about unintended consequences in the output. So if you design a circuit and it seems to perform what you're looking for, do you know that it will always perform that way, or will there be certain combinations of one output combining with another that produces unintended consequences?
I think that if you think about the blocks as a hierarchy of blocks, I mean, I was giving sort of the example of a USB controller that's built with lower level blocks. So you can certainly end up having a bug in the code, right? I could misimplement an adder if I choose, but we believe that the blocks we put in are correct, and therefore there would not be unintended consequences.
Okay, good. The next question, what skills do you think are important you look for while hiring quantum software engineers?
An open mind. I think we've seen software engineers that are super smart and we can teach them quantum. We've seen quantum physics PhDs that we can teach them programming. But I think open mind, the desire to collaborate, and an openness is super important to us.
Mm-hmm. Great. The next question from Ahmed. It seems that Classic is a wonderful circuit generator. Are the generated circuits from Classic compatible with the current available hardware, such as IBM or D-Wave, or do we have to do further work on the generated circuits to make them work?
So they are compatible, and the way they are compatible is that the Classic platform generates code in Q# or QASM and so on, and then the next phase is easily to just take that code and compile it or execute it on the machine. So you could do end-to-end from circuit design all the way to execution and get the results on the Classic platform. You do not need to do additional steps outside the platform.
Okay, great. So just last few questions. Can we use this method to simulate quantum field theories where we have an infinite number of degrees of freedom?
I don't know. I have to.
Okay, it's too technical. All right, that's fine. No worries. Can we send our circuit of large qubits, a large number of qubits, to different quantum computer processor, or only few processors will support this?
So I'm trying to see if I understand the question correctly. So obviously, if you want to run it if you have a 20 qubit machine and you've generated a 27 qubit circuit, then that wouldn't work, right? But as long as you say, hey, my constraint is this number of qubits, for instance, then yes, it will work on different machines that support that.
Okay, thanks. And the last question from now, does Classic also give gate level access when needed? It's a question from Rupesh.
Yes, and I think you can do it in multiple ways. First, you can certainly take the Q# or QASM code that we generate and modify it yourself. The other thing you could do is you could insert your own functional blocks on how to do the implementation. So for instance, let's assume that you wanted to have a multi-control gate. And let's assume hypothetically that we don't have multi-control gate in our code, then you can create a code block that does that. and then use it this way. And when you create that multi-control block, you have gate level. You can even import a small custom program that does that. So we do give you that gate level control on multiple levels.
Okay, that was the last question for now. Or maybe there are some new questions at the moment.
So how about we do this? Let me show you how this works in real life.
Yes.
And then happy during and after to
Okay.
take additional questions.
Perfect. Thank you. Let's
Sure
go
thing.
on.
So what I'm going to do now is I'm going to share the screen, well, we'll see what happens. And so the first thing I'd like to ask you, Pawel, is do I need to make the font larger? I want to make sure that everyone can, or is this too large?
No, for me it's fine.
Is this also okay?
I agree. That was readable. Go back one more. That was readable.
This one?
Okay.
Yeah, that one looks really good.
Very good. All right. So let's work this way, and please, if you can't see it well, then tell me, and I'll try to zoom in. So what you see here is sort of our code in the VS Code in the Visual Studio Code environment. And so let's start with a relatively simple block. So state preparation is sort of fundamental to a lot of quantum algorithms. It's basically initializing the qubits to known values. So here we have a state preparation block. You can see it says state preparation. And I've got 8 values that I want to load as probability mass function. So 8 values, I need 3 qubits. I want to generate a circuit that has 4 qubits. So I'm essentially allowing for 1 auxiliary qubit to make that happen. And here's another very interesting thing, or at least I think it's interesting. We define the error metric. How accurate do you need these to be? So for instance, when you load 0.27, should it be the way I define this now is 5%, it would be 0.27 plus or minus 5% of 0.27. So let's assume that's the circuit. And now I'm going to hit generate. And now it's going to send it to our backend, to the cloud. This is live, right? So if it doesn't, so sometimes it's going to take a little bit longer. But here's the circuit that it generated. So it's a 4-qubit circuit, and that generated this is like a music score, right? So it starts from the first top, and then it goes to the second set of 4 lines. And here on the right side, I'm going to close this just to make more room. Here on the right side, you can see the open custom code that I generated just now that achieves this circuit. One of the interesting things I could do here is I'm going to analyze this. I'll show you some even nicer analysis in a second. But when I analyze this, you see that it says, okay, the circuit that you created had a depth of 32. It had 45 gates. It had 18 multi-qubit gates. These were the native gates that it used, and so on and so on. So now I can go as a designer and say, okay, well, this is very nice, but let's assume that my hardware supports more than 32 deep. I'm comfortable that I'm going to, so maybe I could just increase the accuracy. So instead of 5% error, I'll define 1% error, right? So I changed just 1 digit, 1 line, and said, now generate a different circuit for me. Generate a different circuit for me that meets this 1%. And now, here you go. You can immediately see that it's a longer, deeper circuit, right? The first one had just 2 lines. This has 4 lines. But now I've created a really quick circuit that does that. Let me just take this one step farther and I've got a lot of different demos, but let's take this Oracle demo. So I think this is something that I was showing you before in the slides. I want to do a Grover search. I have the expression here, A plus 5 XOR B modulo 8 equals 2. A is a 3-qubit register, B is a 2-qubit register. I've specified the output as QASM. I'm saying I want 15 qubits and the max depth of 200. And now I'm going to generate that circuit. And let's call it Grover DC, just because this is where we are. So now it's sending that code to the cloud. It's and here's the circuit, right? So you can basically see, I'll close this in a second. Here is the QASM code that implements this. Here's the circuit itself. You can see that it has an adder block because remember I had A plus 5 XOR B modulo 8. So it had an adder block, it had XOR, and then you see the diffuser for the Grover search. Just to demonstrate something else here, I can change the output to, instead of QASM, I can say, let's do it in Q#. So I'm going to generate the same circuit, but do it in Q#. And then I suspect that in a few seconds on the right side, we will have Q# code. So here's the circuit, looks essentially the same, but now you've got Q# code over here that implements the circuit. You can see that it is 470 lines of Q# that I was able to generate on the fly with this kind of circuit. Let me close this and look to something else that I think is even nicer. Here's a crazier circuit in terms of the arithmetic function, right? I've got and there's a reason I want to show you that. I'm going to generate this and call this DC arithmetic. That may take a few seconds, but let's see what happens. I see that Karim raised his hand. Karim,
yes.
let me get to you as soon as I. But go ahead, please.
Karim, would you like to ask your question now? If so, please unmute yourself.
Hi, can you hear me?
Yes,
Yes.
yes, we can hear you.
Thank you. So let me be quick. Can we simulate any number of qubits? Let's say, for example, like 200 qubits, but it just depends on the the simulator, for example, like Qiskit or Q# or whatever it is.
It depends on the simulator. So we can generate a circuit for 200 qubits, but to simulate, that depends on what simulator you have available. You may have an NVIDIA GPU-based simulator that can go faster. You may have an IBM simulator and so on. So let's go back to this circuit. So I generated this circuit and you say, well, what's going on? So let me show you what's going on here. I
actually have another small question.
Please.
Okay, I'll speak quick. Do you plan to support QASM 3 so that, for example, if I want to do like a mid-circuit measurement, okay, and then to check like for the classical register to have like a specific value and then do some operations and then I do a reset over that qubit and do another operation on the same qubit. Can we do something like this? QASM 3 right now supports such operations. So is it available in Classic?
I don't think it's available at the moment, but I would bet that we definitely plan to support it.
Okay, thank you.
So we generated a circuit. You may remember we called it DC arithmetic. And let me open this. And I'm going to open an interactive circuit. This is going to open in a browser. So I will change my share. I will change my share so you can see the browser. Where is Zoom when you need it? Okay. Okay. So here is. Can you see that big block here? So here is the circuit that we generated, and now let's dive in. So I click the plus, and I see all these components that were generated here. So you can see adder, a bit end, and XOR, and so on. Now I could say, okay, let's dive into the adder. Oh, there's a QFT adder. Let's dive into the Q. And by the way, there's a QFT adder, and here's the QFT dagger, so that the cleanup of the adder. I can go deeper and deeper. So I want you to understand sort of two things here. One is that this ends up being a pretty complex circuit that, I don't know about you, but personally for me, that would be really difficult to create. But two, that even though we created this circuit within less than a minute, you can now dive in and actually see how we did it and say, oh, I like this, I don't like this, I want to change the constraints, I want to do something else. So we can give you both sort of the high level functionality to create the circuit, as well as allow you to dive deeper into what it looks inside. Let me show you an example of changing the constraints. So earlier we saw, you can see my VS Code screen, right?
Yes, we can.
Yes.
Perfect. So earlier I showed you the state preparation block. Now let's take an example where I have multiple state preparation. So here is I've got, it's a little bit like before, but many times more in the sense of I had a state preparation block. Here's one block. Here's one such block. 8 probability mass functions, so 3 qubits. This block will take 4 qubits. But then I have 5 similar blocks. So 5 blocks where I'm trying to initialize 3 qubits each with 1 auxiliary qubit. So initially, I'll say, okay, why don't we give it 20 qubits and see what happens. I'm going to generate that circuit with 20 qubits. That is, I mean, it's nice that it works, but it's relatively boring because you can almost imagine what the circuit looks like, right? You can see here, I'm just make it larger. So you have Q0 through Q19. So I've really achieved sort of the 20 qubits that I wanted. And you can see 5 lines that sort of look, or 5 blocks that look the same, right? Here's the first group of 4, here's the second group of 4, third, fourth, and fifth. So that's pretty easy. I initialize 15 qubits with 5 auxiliary qubits. But now here's, let me do something else. Let me change the constraint from 20 to 16. So now I'm trying to initialize 15 qubits with just 1 auxiliary qubit. How can this be done? I don't know. Let's find out. So I'm just I changed one line. I'm going to run the synthesis engine again. And now you're seeing a different circuit. And I'm going to zoom in and try to explain what's going on here. So on one hand, you can say, yes, this looks like a 16 qubit circuit, Q0 through Q15. But now you only see 4 groups. Well, but I asked for 5 groups. So what ends up happening if you start exploring the circuit in greater depth is that the system first initialized 4 groups of 3 qubits each, but then it performed cleanup, uncompute on the auxiliary qubits, and then it used those to initialize the 5th group. So I was able to set values for 15 qubits just using 1 auxiliary qubit because the system was able to sort of figure out how to make that happen. By the way, if I try to initialize 15 qubits with 12 qubits, I just changed the constraint to 12. If you point your attention to the, now you see constraints are unsatisfiable. Our system, at least, was unable to find a 12 qubit solution to initialize 15 qubits. That's obviously not very surprising. One last example. Here's value at risk. It's a financial function. So 8 qubits, max depth. I want to have a finance block. I want to have a Gaussian distribution. This is all parameterized, right? How many qubits do I have? What the default probabilities? I want to calculate value at risk with a certain threshold. And then when I generate that, it's going to run for a few seconds and then give me the result. I could, just like I showed you before, I have both the CASM output here on the right, as well as something that I could drill down deeper inside. One other nice thing, well, there are many other nice things, but one other nice thing I wanted to show you. Earlier, I showed you these 5 blocks of 3 qubits, the 20 qubit state initialization. I'm going to change my screen to a browser that gives you even a little bit nicer graphical analysis. So here you have, it's a little small, but you see these 5 blocks here. You have here the analysis, how many gates, how many multi-qubit gates, what's going on. Here, this gives you analysis of other things. So it shows you how the qubits are connected. So we had 5 groups of 4 qubits each that are sort of more intimately connected. So that's why you see 5 clusters here. If I try to run it on an AWS Aspen 10, this is what the hardware connectivity is. So on the hardware, 20 will be connected to 727 and so on and so on. I can even see the heat map and the gate count. So I can see things that are sort of more focused on the hardware level to help me figure out if I'm doing the right thing, if I need to optimize something, what's the connectivity going to be like on my on the actual hardware, and so on and so on. So happy to go into additional detail or see if there are any questions that I did not answer until now.
Okay.
One.
Yeah, there's one from Itamar, I guess. Itamar.
Yeah, the one is that is almost invited question here, and you compared at one point, you made a comment on one of the generated circuit as difficult. So is there a practical way facilitated here in Classic to evaluate or compare or to give a score to a generated circuit?
Well, I think for us, it's almost like if we met the functionality and we met the constraints, then we're happy. I mean, almost think about a basketball game. You shoot the ball into the basket. If the ball goes into the basket, then I don't really care if it was swish, nothing but net, or it hit the rim or hit the backboard first and so on. If it's a basket, then it's a basket, right? So in this case, we say, look, we delivered the circuit that had the functionality you're looking for and meets the constraints, so we're happy.
Okay.
You have a minute for another question?
On that particular constraint side of things, in future, do you have, looking at it from a general constraint type of situation, like, for example, you could look at, does my circuit consume more energy? Does the circuit, is it more expensive? Can it be optimized at a lower level? Those kind of things. Are those problems under play, or your goal is just as long as it meets the constraint, then here it is. That's what it is. Is that?
No, I think that's a great question. And our constraint engine can certainly look at multiple different constraints. So for instance, if there was tomorrow an API that we started using that said, this circuit is going to cost X dollars to execute on bracket, then we could optimize for the cost, right? You could say, oh, I need the cost to be less than a certain number. So we're not limited to number of qubits or these gates or so gates. We can certainly add additional constraints and make it more sophisticated, such as the examples that you gave.
Thank you.
All right. Do we have any more questions?
Yes, I have one. Can you hear me?
Yes.
Okay. You made a really strong, it's very informative presentation. You made a really strong case, which I think your intention was, for a business model of this, that it's worth it for a company to engage with this? I mean, just seems obvious. It makes sense, right? How could they not lose and not benefit from it? But is anyone else doing something like this? Are you unique in the field? Because I would think there's a lot of customers who would say, yeah, let me try this. It makes a lot of sense. That's what I'm trying to say, I guess. So I would think are there other approaches, or are you like inventing the field, as it were, or this area?
I think we are pioneering the approach of this functional programming for quantum computing. So we've certainly seen the analogies of the electronic and circuit design. So in terms of high-level description language, and they exist in other fields. When you look at quantum computing, there's different business models, right? There's one like the gate level programming. Hey, do whatever you want in the gate level. There are companies, very good companies, that offer you consulting. Don't worry about it. Just tell us what your problem is, and we'll solve it for you. There are companies that actually go at a high level and say, we just focus on quantum finance. So the fact that we use quantum is immaterial to you. Just give us the problem, option pricing,
right,
portfolio optimization, we'll do that. We think we have a unique approach, but
like
happy to hear the group's feedback. Let's make this a discussion. I don't know if Mark Jackson.
No, I think you made a really strong business case for it.
Thank you. Appreciate it.
All right. Do we have any more questions, Yuval? I don't see more questions now on our chat. Yes, Yuval, would you like?
I have one, but
yes,
maybe
go on.
for later. You mentioned that in one example that you did the quantum solution to SAT 3.
Yes.
Which is NP complete. And now the question is it only one special example, or your way is now a solution to a lot of NP complete, which are theoretical, but practically you offer a solution?
I mean, there are a couple of ways to solve SAT, 3-SAT or NSAT problems with quantum. One of them is with a Grover search. The other is defined as an optimization problem. So yes, we can create circuits, quantum circuits, and execute them and find a solution to these kind of problems. And I'm certainly not going to make a claim about any NP complete, and we're not inventing quantum algorithms. We just make it easy to take an existing quantum algorithm and turn it into a working optimized circuit.
Well, congratulations, but it's tempting to use your approach, or the approach that you demonstrated, to many other and maybe more important NP complete.
So happy to work with you, or happy to work with customers on trying that.
Sounds good.
Okay, perfect. So in the meanwhile, one more question appeared on our chat from Jan Blomart. How will you address the need for mixed computing, classical and quantum?
Yeah, that's a great question. By the way, I'm showing the slide just because it has my email address, yuval@classic.io. If anyone wants to ask questions offline, I'm happy to do it. The way we address the mixed computing even today, and I'm just trying to advance to that relevant slide, is by offering the Python SDK and not just the VS Code version. Because when you work with our Python SDK, then you can certainly integrate it with other non-quantum Python libraries. So it could be as simple as, I just need data input, or I need graphics, or I want to integrate with Pyomo to get a model of optimization problem. But one simple example that I did, and we posted a little video on it, when I looked at the I showed you the state preparation example where we changed the accuracy and got different depth of the circuit. So just for fun, created a simple Python loop that ran the circuit generation 20 times with different accuracy level, found what the depth of the circuit is, and then graphed it and say, okay, well, if you need this depth, if you need this accuracy, this is the depth. And basically that allow you to find the operating point. So it's a very, very simple integration of classical and quantum computing. But the short answer is, because we have a Python SDK, you can integrate classical libraries as well and provide a full hybrid solution.
Okay. Good. I hope that it answers the question from Jan. There are two more questions. I think that we still have time, Yuval, so I will ask at least
Please.
one of them. Finding a correct solution to a finite instance of a problem that is NP complete in the limit of large N has no bearing on solving the NP complete problem. So I guess that it's rather a comment, probably from Tom Marshall.
Yeah, just a comment addressing the previous question. Sorry.
Okay, yeah, that's
Go
fine.
ahead, Tom. Nice to see you.
Yes, thanks for the comment. So the last question from Vapeup: how do we follow up on sandbox and learning opportunities on your platform?
Either send me an email, yuval@classic.io, or fill the form on the website, and we'll get back to you.
Okay, perfect, great. All right, I don't see more questions on our chat. Maybe someone would like to unmute himself, herself, or and ask last question.
Well,
If
it's been
not,
a lot of fun for me.
yes.
Sort of a mental exercise on the Saturday.
Yes.
Yeah,
I think that's sufficient. So I think we can finish for today. So Yuval, first of all, congratulations and thanks for a really fantastic talk. So even based on the number of questions and the discussion that followed, we can see that it was very interesting and informative to all the participants. So thank you. And there are many words of thanks on our chat. So yeah, also some questions were quite technical and not trivial, and you managed to answer them very well. So that was great. I believe that we all learned a lot. So yeah, that was very good time for us. So thank you once again. And what else I can say? So Yuval has shared his email address. So if you would like to stay in touch, you can follow the website of Classic or just send an email to Yuval and ask more questions. And we've already introduced at the beginning our future events. So we hope that we'll have opportunity to meet you next time on our next meetings at the end of January and later in February. So Yuval, thank you once again. And since this is the first meeting in 2022 year, I would like to wish all of you all the best, many interesting and inspiring events on your quantum computing endeavor, and all the best. Take care and stay healthy in this difficult pandemic times as well.
And happy to connect on LinkedIn as well if anyone is interested. Yeah.
Great. We hope to see you. We hope to see you next time.
Of course. Take care. Bye-bye.
Thank you. Take care.